The governing equation of motion is derived from the force being pushed on the bike. We have a gravity component, a rolling coefficient component, and a drag force coefficient component. We can divide by mass and get our x double dot position, which is our acceleration for our governing equation. This equation here defines our angle at which the bike is leaning over. It's dependent on velocity, gravity acceleration, and radius of turn.
Here we have our first block diagram. We have our inputs first, and in this situation, because there's no controller, this would be the first applied force or gravity. And because we have no control of the feedback, then the output would be the bike's natural tendency to fall over.
The system without a rider is very unstable. All the trajectories are not converging. If you look at the graph, you can see that the starting positions with different velocities do not end up in the same position, and because it's very chaotic, we don't know where the final position is going to be.
To address for feedback, we now include a rider. The rider can then input to the system motions that are derived from his senses that will then allow him to go in the desired direction. The output of the system here will be the resultant motion of the bike that will take the rider to the desired direction. Now looking at the phase state graph with a rider, you can see that the input velocity is irrelevant because the rider can adjust after feedback to find the desired location. So no matter what velocity the rider begins at, he can then end up at the same location. Here we have an x value of 100.
The force of the bike produced by the rider and the magnitude or direction of that force is what the rider can measure using his or her natural instincts. This feedback, or the rider's instincts, can then be used by the rider to make adjustments such as slowing down the bike, speeding up, or turning. The human rider acts like a PID controller using his or her brain to specify inputs and respond correctly to feedback in order to find the desired output. The performance metrics being used are the time, position, and velocity. Using those metrics correctly will allow the rider to get to his desired location without overshooting. Without a rider, the bike not only will under or overshoot, but it cannot find a desired location either. But with the rider, the bike can attain the specific location and control over undershooting. Without a controller in the bike scenario, the bike begins in one coordinate frame and then will eventually end up in a different frame with the z value being 0 in all cases. With the rider on the bike will remain in the same coordinate frame because the controller will cause the bike to remain pedaling in the same direction. This frame has the rider as the origin.
Here's an example analyzing performance without and with a PID controller, or in this case, a rider. If you look at the red line, the final position is achieved much quicker than without a PID controller and with less overshooting. The y-axis, or the desired value, can be whatever the rider wants: velocity, position, lean angle, or whatever is desired.